Today I'm going to be talking about transport in bilayer graphene, and this is some joint work I've done with my supervisor, Stephen Simon, and a postdoc, Zhongwen. So let me start off with some motivations. In ordinary metals, momentum galaxy scattering is the dominant source of scattering for the electrons. So these are scattering events such as electron-phonon scattering or electron impurity scattering, where the momentum of the electrons is not conserved. But I'm interested in a different regime today, the so-called electron hydrodynamic regime, where in fact electron-electron scattering is the dominant source of scattering for the electrons. And in particular, it dominates over the momentum relaxing scattering. And furthermore, we were inspired by some recent experiments on suspended bilayer graphene, and we were interested in understanding these experiments and seeing whether the experiments are in this hydrodynamic regime. And to do that, we're going to compute the electroconductivity of bilayer graphene using the semi-classical quantum Boltzmann equation and compare to these experimental results. So the starting point for this, of course, is the band structure of bilayer graphene. And you can get it just by doing a simple tight binding model with some interlayer and interlayer hopping. And you find these four bands, but in fact, for our purposes, we can just focus on the two low energy bands that have this band touching point. And we're going to focus on the case where the chemical potential is close to the band touching point. So that's this condition that beta mu is less than 1, where beta is inverse temperature. So then we can write down the quantum Boltzmann equation, which is an evolution equation for the distribution function of the electrons. So the distribution function tells us the number of particles of a given species at a given momentum, where the species is plus or minus 1, depending on whether you're talking about the valence or conduction band. And so the quantum Boltzmann equation looks like this. We've got the time derivative of the distribution function, and on the right-hand side, we've got the collision integral. And the collision integral is really where all the physics is coming in. And so this in general is quite a complicated expression. And of course, we need to ask, when is this approach valid? Because it's a semi-classical approach. And so we require the scattering to be weak in some sense. To be more precise, we need the mean free path to be much larger than the de Broglie wavelength. And it turns out that an equivalent condition is that inverse temperature times scattering rate has to be much larger, much less than 1. And the small parameter that governs this is 1 over NF, the number of fermion flavors, which is 4 in our case. We've got 2 spin species and 2 valley species. And so indeed, this is much smaller than 1. And so the semi-classical approach is going to be valid. But solving the quantum Boltzmann equation turns out to be a rather tedious numerical task. And so it's nice if we've got some more intuitive model as well to understand the physics that's going on. And in fact, such a model exists. It's the so-called two-fluid model, which can be derived from the quantum Boltzmann equation just by taking its moments. And we've got this description of the two fluids, the electron and the whole fluid, in terms of their mean velocity. And we write down the two evolution equations for these mean velocities, and you get 3 terms on the right-hand side. The Coulomb drag term, which switches on when the electron and the whole fluids have different velocities and exert drag on each other. There's the momentum relaxing term, which is just like a Drude-like term. And finally, we've got this driving term due to the applied electric field. And there's one thing I want to emphasize about these two fluid equations, which is the presence of a long-lived momentum mode. So if we've got this momentum mode where electron and holes are moving at the same velocity, then of course the Coulomb drag term vanishes, and this momentum mode is relaxed on a much slower timescale, which is this momentum relaxing timescale. And so we can consider the extreme limit where the momentum relaxing timescale goes to infinity. And in this limit, there's three important consequences. First of all, the electrical conductivity at charge neutrality is still finite in this limit because the momentum mode doesn't carry any charge. We've got electrons and holes moving at the same velocity. They've got the same number density, so there's no charge carried. But as soon as you go away from charge neutrality, the momentum mode carries charge, and so your electrical conductivity diverges. Similarly, the thermal conductivity always diverges because the momentum mode always carries heat. And so if we take the appropriate dimensionless ratios, we've got this ratio of electrical conductivities which diverges. So it tells us that the electrical conductivity increases very quickly away from charge neutrality in this clean limit. And we can also compute the ratio of thermal conductivity to electrical conductivity, which is the so-called Lorentz number. And because the thermal conductivity diverges at charge neutrality, the electrical conductivity does not, this ratio will diverge in the clean limit as well. And so we see that we've got this large Wiedemann-Franz law violation at charge neutrality. And so these two features are essentially signatures of hydrodynamic transport. So let me now show you some of the experimental results by a group in Geneva on suspended bilayer graphene. And what they've done is they've measured the electrical conductivity as a function of number density and temperature and plotted it in terms of this dimensionless quantity beta mu, inverse temperature times chemical potential. And I want you to notice two things about this data. The first of all is that the electrical conductivity increases very quickly away from charge neutrality. This is consistent with the hydrodynamic regime, as I explained on the previous slide. The second thing I want you to notice is that you've got the scaling collapse. They've measured this for different temperatures, and all the curves for different temperatures collapse when plotted in terms of this dimensionless parameter. And this, in fact, tells us something about the momentum relaxing mechanism. So remember that the ratio of conductivity away from charge neutrality to conductivity at charge neutrality is essentially given by this ratio of scattering rates. And the fact that it doesn't depend on temperature tells us that this ratio of scattering rates cannot depend on temperature. Now, if we look at how these scattering rates scale with temperature, well, electron-electron scattering is just proportional to temperature. Then there's three possibilities for what could be causing the momentum relaxation: electron impurity scattering, electron phonon scattering, or scattering off the boundary. And it turns out that it's only phonon scattering that scales in the same way as electron-electron scattering. And so this tells us that looking at the experimental data, we see the scaling collapse, and from this we deduce that electron phonon scattering must be the dominant source of momentum relaxation. So let me just show you the results from the quantum Boltzmann equation compared to the experimental data. So you see that the solid black line, the quantum Boltzmann equation, approximates the experimental data very well. And furthermore, the two-fluid model approximates the quantum Boltzmann equation very well. So we can use the far simpler two-fluid model instead of the more complicated quantum Boltzmann equation. So let me conclude at this point. So I've explained how suspended bilayer graphene exhibits hydrodynamic transport. I've highlighted two signatures of hydrodynamic transport: the sharp increase in electrical conductivity away from charge neutrality, and the violation of the Wiedemann-Franz law at charge neutrality. And the first one has been observed in experiments. The second signature has not been observed in bilayer graphene. It has been observed in monolayer graphene. And so furthermore, we've got this separation of scales. The hydrodynamic regime means that electron-electron scattering must be dominant, and the subdominant scattering is electron phonon scattering, which we saw with the scaling collapse of the data. The quantum Boltzmann equation seems to approximate the experimental results very well, and furthermore, the quantum Boltzmann equation results are well approximated by the two-fluid model, which is much simpler.